Now looking at Simpson's rule. So this is another approximation method. So the first one is the trapezoidal rule, which is h on 2, and the multiplier pattern is 1, 2, 2, 2, as many 2's as you need in the middle with a 1 on the end, okay? And we know why the rule is like that, because when we derive the rule, the first trapezium and the last trapezium, the very first and the last don't get repeated, don't get doubled. Okay. Now Simpson's rule is generally more accurate than the trapezoidal rule because it makes use of parabolic arcs. So instead of this being a straight line, it'll be like a parabolic arc as opposed to a straight line here. All right. So therefore it will generally be more accurate. Okay. So if I've got, many sub-intervals here, remember that the number of function values, again, that the number of function values is one more than the number of sub-intervals, n. Same as for the trapezoidal rule. So this is b minus a over n. Remember, I've just got dots here because there could be many sub-intervals. So these are all the sub-intervals. But this is y0, y1. So if this is x0, x1, x2, x3, etc., xn, x to the n minus 1, x to the n minus 2, I'm just saying that's what we do with the first one. It's called y, at x0, the y value is y sub 0. This is x sub 1, y sub 1, in other words, subscript. This is y2 value, this is y3. The last one will be yn, y to the n minus 1, y to sub n minus 2, sorry, okay? So the reason I'm just putting those, I don't use this formula anyway, but I'm going to show you the formula because you'll see it, okay? Notice, so the integral, basically the area under the curve, right, is equal to the integral between b on and a of the function of x, if this is my function of x, dx. Now, the approximation is, it's h on 3, y0 plus yn. Notice it's the same as trapezoidal rule in that the first value and the last value aren't multiplied by 2 or any other number. And then it's 4 times y1, y3, y5, etc. So we call it 4 times the odds, and it's 2 times y2, if I put in y4 there, 2 times y2, y4, etc. So it's called the first and the last plus 4 times the odds plus 2 times the evens. But the thing is, the first value is called y0, not y1. And the last one is called yn, y sub n. So that one there is y1. So it's 4 times the odds and 2 times the evens. Now, I don't really learn that formula like that, okay? I mean, you might say, yep, I think I can remember it. It's 2 times the evens, even numbers are divisible by 2, it's 2 times the evens. But what I use is the multiplier pattern. So what I do, I say, I just remember trapezoidal rule uses only 1's and 2's. Simpson rule uses 1, 2, 3, and 4. So this is how I remember it, that the Simpson's rule, is the more accurate rule. So it's a little bit more complicated. It uses 1, 2, 3, and 4. Whereas the trapezoidal rule only uses 1 and 2. So the way you remember it is area is approximately equal to h on 3. There's your 3. And your multiplier pattern is the following. And the multiplier pattern, you use it in a table of values. You know how the first and the last are just one of those? So multiplier pattern is 1 for the first one, 1 for the last one. Got it? And then you know how the other one goes 1, 2, 2, 2, 2, as many 2's as you want and a 1? This one's different. It does use 2's, but it goes 1, 4, 2, 4, 2, 4, 1. But it depends on how many values we've got. So this is our multiplier pattern. Now, I'm going to show you the multiplier pattern for... Now, the thing with Simpson's rule is that you must have an odd number of function values. I'll show you why. So let's look at the multiplier patterns. So multiplier pattern. So if you've got 3 function values, so if we've got 3 function values, it means you've got 2 subintervals. See, 1, 2, 3 values, right? The multiplier pattern for 3 function values, the formula is area is approximately equal to h on 3. 1, you have to have 4 next, but I'm not going to be able to fit in sorry, 1, 4, 1. You must have a 1 and a 1 on the ends, and it's supposed to go 1, 4, 2, 4, 1. But if you've only got 3 values, you can only have 1, 4, 1, because the 4 has to come after the... Because I'll tell you why, because this would be y0, y1, yn. Because always your first one is y sub 0, your last one's y sub n, and your middle one, your next one would be y1. See how it's 4 times the odds? Well, there's no evens, so we can't have 2 times. If you've got 5 function values, so for example, you would have 1, 2, 3, 4, 5, whatever it is. You've got y sub 0, y1, y sub 2, y sub 3. I'll call this one y sub n, because always the last one's n. Your multiplier pattern is, A is h on 3. Sorry, I should be putting the y's at the top because they're the y values, but you know what I mean? It's h on 3. This is where you go 1. It's always 1, 4, but I can fit a 2 and a 4 and a 1. So it's 1, 4, 2, 4, 1. So if you've only got 3 function values, now why does this work? Because it's, if you look at the formula, it's y0 plus yn, so they're multiplied by 1. It's 4 times the odds, so 4 times y1 and y3. See, 4 times y1. See, this would be the y0, and this is the yn. This is the y1, y3, and 2 times the y2. Do you get the idea? So, and it's 2 times the evens. So you tell me for 7 function values what the multiplier pattern is. A is approximately equal to h on 3. Go. 7 function values. 1, 4 has to come next. What's next? 2, 4, 2, 4, 1. You keep alternating. So how many have I got? 1, 2, 3, 4, 5, 6, 7. That's the multiplier pattern for 7 function values. And I'm sure you'd know the multiplier pattern for 9. 1, 4, 2, 1, 4, 2, 4, 2, 4, 2, 4, 1. So therefore, you must have, with this, must have an odd number of function values for the trapezoidal rule. Oh, sorry, for the Simpson's rule. Whereas with the trapezoidal rule, you don't have to. It could be odd or even number of function values because it's 1 and as many 2's as you need and 1 on the end. So this one the same, 1's on the end, h on 3. You can see you use 1, 2, 3, 4 unless there were 3 function values only. All right, so this is very similar to what you've just done, just a different multiplier pattern. So notice 2 subintervals here, 1, 2, 3 function values. Got it? 4 subintervals, which is 4 spaces. 1, 2, 3, 4, 5 function values. Don't worry about this 3 applications business. All right, I don't do it that way. If we've got 1, 2, 3, 4, 5, 6 subintervals, 7 values. It's like when you build a fence. You know, you need 1 pole on either side to make 1 section. All right. So 6 subintervals, 7 function values. Okay. So we're going to do this question, but we're going to do this one with 5 function values instead. Okay. Approximate to find. Use Simpson's rule with 5 function values to find the integral between 3 and 2 of root x dx. What we're going to do, we'll do it this way. And, you know, we can actually integrate this if we wanted to, and we're going to see how close we get. So, if you want 5 function values, how many subintervals is that? 4 subintervals. That means that n, in other words, n is 4. So what's it going to go up by? So you've got to work out what it's going to go up by. Now this is the formula, the graph of root x. I mean, you don't have to know what it looks like. But if you want 5 values, I'm going to put a 2.5 in the middle. That's 3 values. What do you think is going to go here? What do you think? Anyway, if you're not sure what it goes up by, h is b minus a on n, and your b and your a, that's 3 minus 2 over, n is the number of subintervals, not the number of function values. So 3 minus 2 on 4, and it goes up by quarters. So h is 0.25. Because if I've got 1, 2, 3, 4, 5 function values, and I've drawn in 5, it's got to be 2, 2.25, 2.5, 2.75, 3. Okay, so it goes up by quarters. So what's my formula? Area is, wait, before I do my formula, I need to do a table of values. Always do a table of values. X, function of x. When x is 2, 2.25, 2.5, 2.75, and 3. Now, what you can do, why don't you just write it as root 2, root 3, root 2.25. Don't write down what they are to so many decimal places, because you're going to have too many rounding errors. Function of x is root x in this case. So what I've done, we've done a table of values for each x and y value. And these are your function values down here. And then we put the multiplier pattern underneath, and I go times 1, times 4, times 2, times 4, times 1. And then I write out my formula. Area is approximately equal to h on 3. Now, and then the multiplier pattern, but my h is 0.25 over 3. And then, don't I just do this one plus this one, root 2 plus root 3, plus, see what I'm doing? 4 times root 2.25 plus root 2.75 plus 2 times root 2.5. That's it. Be careful with the brackets. So you need a bracket here, add these ones individually. You know what I would do? This 0.25 divided by 3, do it at the end. So do all this inside first and then times it by 0.25 divided by 3, which is actually a quarter divided by 3, which is 1/12. Or you just divide that answer by 12. So off you go. Try it. We're getting 1.58 to 2 decimal places. Now, you know, with this question, that was an approximation. See how root x is a parabola and Simpson's rule uses parabolic arcs? This approximation will probably be very close to the exact value is. So if we were to integrate, I'm just going to do this with integration. So now by using integration, just to check my answer, see how close it is, let's just do the integral between 3 and 2 of root x dx. Isn't that the integral between 3 and 2 of x to the half dx? Which is, we're just going to compare it. You know, and I could actually do a quick trapezoidal rule to compare as well here, because I've got all the function values. I may as well do a quick trapezoidal rule as well. What do we get? X to the that's a half, so 1/2 is 3 on 2. So x to the 3 on 2 over 3 on 2 is 2/3 x to the 3 on 2, substituting in the values of 3 and 2. That's 2/3 square root of x cubed, substitute in the values of 3 and 2, which is 2/3 times root 3 cubed minus, you know, you could even take the 2/3 out. How do you feel about that? Taking the 2/3 out, you don't need it in the substitution. You could go 2/3 bracket root 3 cubed minus root 2 cubed, or you can put the 2/3 in twice. But don't worry, we'll do more of that later. I haven't put the bracket yet. But later you'll find it's easier to pull the 2/3 out and then just do the substitution on, because this is really, look, I will pull it out. That's 2/3. Root 3 cubed is 3 root 3. I've pulled the 2/3 out, and root 2 cubed is 2 root 2. So that's the exact. So anyone, what have you got? 1 point what? As your?
Yeah, we got 1.7,
Exact 1.58. Yeah. There you go. Because Simpson's rule uses parabolic arcs, and that's actually a That's a parabola. That's as a half a parabola. So Simpson's rule would be a very, very, very good approximation to this. We'll use Simpson's rule with 7 ordinates or 7 function values to find an approximation for the integral between 4 and 1 of log of x dx. So we've got x and function of x, so I'll just go log of x. We're going to, let's see what h is. B minus a on n. If you've got 7 ordinates or 7 function values, what does n equal? How many spaces? 6. So it's 4 minus 1 on 6. So it's 3/6, which is a half. So it goes up by halves. So you have to have your x values going up by halves. It starts at 1, then you've got 1.5, 2, 2.5, 3, 3.5, and 4. So we're going log of 1. Just check what log of 1 is, girls. Log of 1.5, etc. 0, yeah. Log of 2, log of 2.5. The rest will be values. Log of 3. Log of 3.5 and log of 4. So they're your function values. And what's your multiplier pattern? 1, 4, 2, 4, 2, 4, 1. It's always symmetrical. Oh, it's palindromic. The multiplier pattern is palindromic. You read it the same forwards and backwards. So please don't ever go, it goes 1, 4, 2, 4, 2, 1. It can't. You've got to have an odd number of values and you've got to read it the same forwards as backwards. Okay? So area is approximately equal to h on 3, which is 0.5 over 3. 0.5 on 3 is 1/6. And then you add the individuals, log of 1, which is 0, plus log of 4, plus 4 times those 3, log of 1.5 plus 2.5 plus log of 3.5 plus 2 times log of 2 plus log of 3. And another bracket. We all good? So I couldn't fit it on 1/9. So the individuals, 4 times those 3 plus 2 times those 2. I wouldn't do, now a half divided by 3 is 1/6, but don't do that. Do that at the end. And we'll get an approximate area. From exercise 2.2, but it's just slightly different because it's saying find the integral between 5 and 2 of 1 over x squared minus 1 dx using 6 subintervals. Now, it's not saying that's how many function values. Subintervals is spaces, columns. So how many function values? So is n 6 or n 7? Yeah, n is 6. N is the number of subintervals. So your h is b minus a over n. 5 minus 2 over 6. Again, it's a half. Okay, so if you've got 6 subintervals, you've got 7 function values because it's, like I said, like a fence. The first section has 2 values, but then each other section you only have 1 additional value. So that will be 6 subintervals is 7 function values. So draw up your table, x and your function of x, or 1 over x squared minus 1. And then your first value is 2, and it goes up by halves, 2.5, 3, 3.5, 4, 4.5, and 5. And in some questions you already have the table, but in others you have to draw up the table. So you want to work out all your values, okay? I'll give you a minute to do those. Whole number ones for 2, 3, 4, and 5, you can just do those very quickly in your head, all right? And then for 2.5, 3.5, 4.5, please write them as fractions. Don't write them as decimals because it's just much easier to enter. Because otherwise you can end up with rounding errors, especially if we want the answer to like 2 or 3 decimal places. You'd have to write them to 3 or 4 at least decimal places. What about 3.5 squared? What do we get? The 3.5 one. Anyone? 4 on? And then this must be 4 on something as well. 4 on? Okay, so multiply a pattern underneath. 1, 4, 2, 4, 2, 4, 1. And off you go with your area is approximately equal to h on 3. which is 0.5 on 3, which is 1/6. And then you can put in your singles, the third plus 1 on 24, plus 4 times those fractions with the 4 on the numerator, plus 2 times the others.
The table goes.
Oh, is it? Yes, of course. 1/8. Sorry, 1/8. Very good. Okay. Should really go, that integral is approximately equal to. Got it? But if they're saying find the area, so I can say the integral is approximately equal to. Right? Yeah. Because integral is area under curve. But they're not asking for the area, they're just saying find this integral. Okay?